So here we go, guys. This is the second example in chapter 7, and this is this section on 7.4 on static rigid bodies. So usual routine, let's go through and pick out the key facts. So here in example 8, we've got a ladder AB, mass M, length 3A, has one end resting on A, resting on rough horizontal ground. The other MB rests against a smooth vertical wall. A load of mass 2M is fixed on the ladder at the point C where AC is equal to A. The ladder is modelled as a uniform rod in a vertical plane perpendicular to the wall, and the load is modelled as a particle, so it can be considered to act at a point on the ladder. The ladder rests in limiting equilibrium at an angle of 60 degrees with the ground. Okay, so we've got our diagram over here. Please add on all the forces. I suggest you draw it a little bit larger than it is here, and we can have a look at the forces acting. I'm actually going to draw that out again below, so we've got space to add everything on that we need. So you have a go, pause, and then have a look at the diagram that I've generated. Okay, here we go. So we've got our wall, and our ground, and our ladder at 60 degrees. We're told its length is 3A and it's uniform, so the mass is going to act at its centre. So we've got a weight acting down there. The mass of the ladder is M, and these lengths here then are 3 over 2A. We're also told we've got a particle at the point C where AC is just A. So this is point A down here, and we've got another mass here of 2M acting downwards, and we've got in here the gap here is going to be A over 2. Okay, now let's look at what other forces are acting. Because the wall is smooth, we've got a reaction with the wall, and there is no friction, so it's just perpendicular to the motion. So we could call that capital X. On the floor here, it's resting on the ground, so it will be trying to slide down the wall and away from the bottom of the wall. So our friction must act towards the wall. So our friction has got to act towards the wall, and we've got a reaction vertically at A. B, and then that was our point C. Okay, so let's go back to the question. Now we've got the diagram and all the forces acting on it. Yeah, this is our wall here. Go back to the question and need to see what we're asked to find. We need the coefficient of friction between the ladder and the ground. So from A, friction is equal to mu R, since equilibrium on point of slipping. Yeah, it's limiting equilibrium, it's on the point of sliding. Okay, so that suggests to us very strongly that the things we need to work out then are friction and the normal reaction. And we've got lots of ways of doing that, or thinking about it anyway. And we've got our standard approaches, resolve horizontally and vertically. And let's begin with those. If you took moments about a point to start with, it really doesn't matter. Yeah, because we're likely to have to do all these things to get at our answer. Resolve vertically. So let's look at our vertical components. What have we got? For our vertical components, we've got RA is vertical, 2M and 2M. Now there's something missing on that diagram, isn't it? It should be 2mg as the force and mg as the force acting downwards. Are there any other vertical components? I can't see any. So we've got RA minus 2mg minus mg equals 0 since equilibrium. So RA is equal to 3mg. Well, that's quite a good start. Okay, so we've got one of the things that we wanted to find. There's our reaction from above. So we now need to work on the friction. Okay, well, it seems to make sense then to resolve horizontally. So let's look at our diagram, pick out the horizontal forces. So we've got X and we've got friction and nothing else. So we get friction minus X equals 0 since equilibrium. So the friction equals X. The only problem is we don't know X. So let's come back to our diagram and have a look at how we might find X. Well, we resolved horizontally, we resolve vertically. So the most sensible thing to me seems to be to take moments about, which point do you think? A. Why does it have to be A? Well, if we took moments about B, we would eliminate X. And so we would end up with the friction in terms of the reaction. And we would get to a correct answer in the end. But I think it's much easier to take moments about A. And then we're going to find X. We've eliminated RA and the friction by doing that. So we're only going to have to find X. So if we take moments about A. Let's have a look then at the distances. So we're going to need the distances from A to the lines of action. Whoops. So the distances to the line of action here from A is going to be A, the hypotenuse. This is adjacent to the angle, so it's cos of 60. There's our line of action. So this is going to be the hypotenuse, A over 3A over 2, again, cos of 60. And then we're also going to need our line of action of X, and our distance to our line of action of X is total length. The hypotenuse is 3A. It's opposite the angle. Well, if this angle is 60 degrees, then this angle is also 60 degrees. It's also 60 degrees. So 3A, and it's opposite the angle, sine of 60. So we're going to get moments about A in the anti-clockwise direction. That's going to come from the X. So that's X times 3A sine of 60. Yeah, that's using these two to give that is equal to. Then we're going to get 2mg times A cos of 60 plus mg times 3A over 2 cos of 60. So that's coming from, this bit's coming from these two forces and these lengths. Okay, so we can now collect like terms. We've got mg cos 60 here, so that's going to be 4 over 2, so 7a mg over 2 cos of 60 equals 3a sine 60 times x. So the a's are going to cancel. We've got x equals 7mg over 6, dividing down by the 3. Cos 60 is equal to, cos of 60 is root 3. Sorry, cos of 60 is a half. So it's cos 60 a half. Sine of 60 is root 3 over 2. So we've got 7 over 6 mg. Divide in by a fraction, we invert and multiply, so that becomes 1 over root 3. Multiply top and bottom by root 3, so we get 7 root 3 mg over 18 for x. So we've now got x, so we've also got the friction. So we can now substitute into, so we're going to sub into friction equals mu r, since it's on the point of slipping. So my friction is the same as x, which is 7 root 3 over 18 mg equals mu and then r, which we found earlier, 3 mg. So the mg's cancel, so mu is equal to 7 root 3 over 3/18 is 30/54. So we tap that in a calculator and we get, I don't know, root 3 is what, 1.7-ish. It's going to be just about a fifth, I would think, about 0.2 and a bit. Tap it in the calculator and we get 0.225. That's to 3 significant figures. That's probably a little bit over accurate, but the g's have cancelled, so we've not actually used the fact that g is two significant figures in the question. Okay, I've already answered part B as we've gone through, because you have to, but state how you have used the assumption that the ladder is uniform in your calculations. Well, we did it right at the beginning of our answer. Yeah, it was the idea that it acted at its centre of mass. Oops, undo that. Yeah,